All right, welcome back, GLS4OM. We are now leaving differentials behind. Some say that might be a bit derivative. My attempt at a little humor there. We are now moving into Unit 6, the integral. And here's your humor for the day. So if you're not sure what Zeno's paradox is, then maybe you can look that up, and then you'll understand what's going on in this sort of line on the bottom and how it's being divided. All right, so what is an antiderivative? You have found antiderivatives before. So if f at x is 2x, now let's say f at x is x squared, then f prime at x would be 2x. Now, what if f prime at x was 2x? Then we're looking for its antiderivative. Then f at x would be the antiderivative. And the antiderivative of 2x, of course, is x squared. But then you'll see we'd have to add any constant. And if you've taken calculus already, try and change the color of the pen there. I'm going to try and draw a parabola there. So why the constant? If I shift this parabola up or down, the slopes of the tangents will not change at specific x values. They will be the same. If I slide it left-right, of course, then the slope of the tangents values will start occurring at a different x value. But vertical shifts up and down will not change the values of the slopes of the tangent at any x point. And also, if you take the derivative of a constant, you'll get back to here. So this is what we're going to focus on this lesson, is this notion of antiderivative. So capital F at x is an antiderivative of f at x if f prime at x is equal to f at x. So we were looking at, I'm going to write it this way now. What if f at x was 2x? Then its antiderivative capital F at x would be the function, let's do this, x squared, because if you take the derivative of f's capital F, you get f at x back. So that's what it means to be an antiderivative. The general antiderivative, I'm just noting for the general antiderivative, we're going to add a constant c to it. And I did mention the bit about shifting up and down that I showed you over there. So the process of finding an antiderivative is known as integration. First half of calculus, you were interested in this. Here's a curve. And it's all about the slope of the tangent somewhere to that curve. Now we are moving on to integration, where it's a little bit different. So I'm going to go back to, I want to make the pen thin. Let's draw a curve. So in integration, it's going to be different. You'll see in the next part of this lesson, we're going to try and figure out how can you find the area under the curve. So the process of finding the area under a curve is the second branch in calculus. It's known as integration. And we use this symbol, the integral symbol, and it's almost like an elongated S. And it's really S because it's a summation, but we won't see that till a bit later on. So the integral of f at x dx is equal to capital F at x plus c. We've just discovered, of course, that f prime at x must be equal to f at x. So let's say we wanted to do the integral of 2x dx. Then we would be the antiderivative x squared plus any constant. And note, we are satisfying that this is capital F at x, and the derivative of capital F at x is indeed equal to 2x, which is our f at x here. And now some terminology, naming of the parts. So this function here, f at x, is called the integrand. The dx on the end is called the differential, and it tells us what the independent variable is. So what are we supposed to be integrating with respect to which letter? We're told that here, it's dx, and c is called the constant of integration. All right, so power rule, I'm going to get you to think about this one. Let's see if you can try this one, going backwards on this one, right? And remember, what are you after? I'm looking for a function, capital F at x, such that f prime at x, capital F prime at x, would be equal to x to the fifth. And in the second example, B, you're looking for a capital F at x, such that f prime at x would be equal to x to the 3/8. So why don't you try to do these two first, and then we'll talk about a general rule for going backwards on if the integrand is a power function. And I'm going to pause just as a reminder that you should be thinking about how you're going to solve this rather than simply watching the video. All right, so let's talk about the first one. So if I want to go backwards and I'm looking for f at x such that, or capital F at x, such that f prime is equal to x to the fifth, then I know I must have started from an x to the sixth, right? But if I then take the derivative of x to the sixth, that 6 is going to come out in front, and I do not have a constant here. So what I'm going to have to do is divide this by 6. So if you take the derivative of x to the 6 divided by 6, you will get 6x to the fifth. Let's just write that out quickly just so that you can see that, divided by 6. And then that will take me back to where I started from. That's what I was asked to do. And then, of course, you have to add any constant. If you forget the plus c, you might lose several marks in university. And, of course, you'll be losing marks here as well if you forget the plus c. All right, moving on to the second one. So hopefully you did the second one as well. I'm going to pause just for a second. All right, so let's discuss this one. So if I'm looking for this capital F at x, when I take the derivative of this, I want to get x to the 3/8 back. That means I must have started with a power function whose exponent was 1 more than 3/8. So x to the 3/8 plus 1. And then when I take the derivative of this, because that multiplier would come out in front, I'm also going to divide by that multiplier over there. And 3/8 plus 1 is 11/8. So x to the 11/8 divided by 11/8 should get me back to x to the 3/8. Now I'm going to invert and multiply, so I'm going to get to here. 8 over 11 times x to the 11 over 8. And notice how when you take the derivative of this and you bring that exponent out in front and multiply these two together, you'll get 1 back, which is what we have in here, 1. And taking 1 away from that will give us 3/8. So you can always check that you have the correct antiderivative by then taking the derivative of this and ensuring that you get the integrand back. And then, of course, don't forget you have to add any constant. The derivative of any constant is 0. So an integrand does not have a unique antiderivative. There's an infinite number of them. They're all vertical shifts of each other. And now I'm going to pause, and I want you to think about what would be the general rule if you're going to go back on when the integrand is a power function. What's the antiderivative of a general power function? All right, so resuming, I'm looking for a capital F at x. And since the degree of my integrand, right here, there's the integrand, its degree is n, the degree of my antiderivative is going to need to be x, or it's actually going to need to be n plus 1. So I've written x to the n plus 1 because the degree of the antiderivative is going to need to be 1 more than the degree of the integrand, because when I take 1 away from this, it's going to get me back to here. And then I'm also going to have to divide by the exponent here, because when I take the derivative of this, I will get n plus 1 times x to the n. And that won't get me back to the integrand unless I also remember to divide this by n plus 1. So the general antiderivative of the integrand x to the n is x to the n plus 1 divided by n plus 1 plus c. All right, let's see if you can come up with the antiderivative of this one, because it does look like it's a power function, correct? We would have x to the negative 1. But if we try to use this power function rule over here, so let's see if we try and see, because it does look like a power function, doesn't it? Then our capital F at x would be x to the negative 1 plus 1, all divided by -1 plus 1. And that would give us x to the 0 divided by 0, which of course is undefined. So try and think about derivatives of special functions that you've done. If you've already taken calculus, you might be able to figure this one out. If you haven't, it might be, I'm not sure how far you've gotten, but this is one of the special functions we learned how to take the derivative of. All right, I'm going to pause to give you time to think. All right, resuming now, the special function that we're after is the natural log of x, because when you learned how to take the derivative of the natural log of x, you ended up with, so if f at x is ln x, then f prime at x is 1 over x. So jumping over here, the antiderivative of 1 over x is ln x plus c, and just showing you that if you move forward, I guess I should put the plus c in there as well. When you take the derivative of ln x, you get 1 over x, and the derivative of c, of course, is 0. So that gets me back to the integrand there. So let's come back to our power function rule, which was here. And maybe we should note this works for all cases, right? We should note n not equal to -1. So it works for all power functions except the power function x to the -1, but that's not a problem because we've now found that its antiderivative is ln of x. All right, see what you remember about the derivatives of trig functions, because these are all derivatives of certain trig functions. So you should be able to go backwards just to think about where did you start from in order to get these. And you'll have to adjust and tweak for negative signs because some of these have negative signs. Again, if you haven't learned yet how to take the derivative of the trig functions, then you could Google this now, or you can just wait for a few seconds. I'm going to pause, or you just keep playing and it'll give you the answer. I'm going to pause now. So those of you who already know how to take derivatives can think backwards. Okay, resuming. So to go backwards on a sine, that means we must have started from a cos. But I remember that if you take the derivative of cosine, you will get negative sine. So that means I'm going to have to tweak this answer. So what I'm going to have to do is the integral of sine x will be negative cos x plus c, because the derivative of positive cos is negative sine, and the derivative of a negative cos would be positive sine. So notice how we're getting the integrand back. This one, we don't have to worry about any sine issues. The antiderivative of cos is sine, because the derivative of sine is cos. So take the derivative, we end up getting the integrand back. In this case, derivative of tangent is secant squared. So taking the derivative of tan, notice we get the integrand back. And notice in each of these cases, we are going to have to add the constant. The antiderivative of cos squared x is going to be negative cotangent plus c. Notice if you take the derivative of negative cotangent, you get cosecant squared x. The derivative of cotangent is negative cosecant, so the derivative of negative cotangent is cosecant. And if we do the integral of secant x tan x, you'll get secant x plus c. And again, if you take the derivative of secant, you get the integrand back. And the antiderivative of cosecant squared cotangent is negative cosecant. The derivative of negative cosecant is cosecant cotangent, again getting the integrand back. You would have looked at the derivative of cosecant, which is negative cosecant cotangent. Slides that are probably important for you to print out and know at this point in time would be this one, the general rule for the antiderivative of a power function, the general rule for the antiderivative of 1 over x, and now on this particular slide, the general rule for the antiderivatives of those trig combinations. Next one up is going to be exponential. Again, if you've already taken calculus, this shouldn't be difficult for you because you're just going to think, what function should I take the derivative of to get e to the x back? And what function should I take the derivative of to get e to the kx plus b? If you haven't taken it already, two choices again, you can pause and Google, or you can just continue watching, and I will give you the answer in a few minutes. All right, so d by dx of e to the x is simply e to the x. The derivative of any exponential function is itself times its stretch or compression factor. So that would be a to the x ln of a. So going backwards on these. The antiderivative of e to the x is e to the x. And then again, we have to remember to add any constant. Again, the derivative of e to the x is e to the x. In this particular case, I'm going to have to tweak or adjust for the derivative of the numerator. Note that numerator is a linear function, so we're really at e to the mx plus b. We've got a linear function there, and the derivative of a linear function will be a constant. So I just need to I need to divide by the derivative of kx plus b, which is, of course, k. And remember, this is, we're going to be using the chain rule when we take the derivative, and sort of go forward on this one here. We need to use the chain rule because this is a composition of two functions. So the derivative of that exponential function would be itself, which is what we have right over there, times its stretch or compression factor, which is ln of e, and then I need to multiply by the derivative of the baby, and the baby function in this case is kx plus b. And the derivative of kx plus b is k. So that's what's happened. Taking the derivative of this function, it should be itself. The derivative of the exponent is k. The k's will cancel, and we get back to the integrand, which is what we needed. Some rules about linearity of the indefinite integral. So if you want to do the antiderivative of a sum of two functions, or the integral of a sum of two functions, you can split it up into the sum of two integrals. So here's the integral of a sum, here's the sum of two integrals. This is the integral of a constant times a function. It's the same thing as the constant times the integral. Those are properties that you can apply. All right, now it's probably time for you to pick up your pen. So we definitely are going to be using these properties here. The integral of a sum is the sum of the integrals. So you can split this up into three separate intervals based on this one, and this one. And this one you could split into this one, and this one. So I'm going to suggest that you actually pause now and see what you can recall. Remember, we know how to take the derivative of power functions, or the antiderivative. We know how to integrate power functions. We know how to integrate trig functions, and we know how to integrate some exponential. We were looking at e to the x. So I'm going to pause as a reminder. It's a good time for you to pause and see if you can figure these out. All right, so taking up the first one. If I wanted to, but I chose not to here. And I think I'm going to pause because it's going to be very slow watching me write this. All right, just explaining, just to show you that I was definitely applying these properties. Whoops. Where are we on here? Yes, I was definitely applying these properties right here. So we have the integral of a sum is the sum of the integrals. Definitely applying that property here. So we could show this step if we wanted to. It's 5 times the integral of x squared dx minus 6 times the integral of 1 over x dx plus 4 times the integral of x to the negative 2/3 dx. Notice these are all power functions. Going backwards on the power function, what we said we should do, finding its antiderivative, we should add 1. So it should be x to the 2 plus 1, which is x cubed, and then we should divide by 2 plus 1, which is 3. This is a power function, but its antiderivative doesn't follow that power function rule, which was x to the n plus 1, all divided by n plus 1. In this particular case, we have a natural log function. So the integral of 1 over x dx is natural log. This is a power function that follows the rule, this last one right here. So it should be 4x to the negative 2/3 plus 1 following this formula, divided by negative 2/3 plus 1. Negative 2/3 plus 1, of course, is 1/3. And 4 divided by 1/3 is 12. So the antiderivative of this would be 5/3 x cubed minus 6 ln x plus 12 x to the 1/3. And of course, we then have to add c. And I'm going to let you think briefly about the next one. All right, so in this one, I am certainly not going to write it all out and break it up like that one. But we have the integral of a trig function here. We have the integral of another trig function here. And this is the integral of an exponential. So we would be using some information from this slide and some information from this slide. And of course, our rules on how to break it apart. So let's look at the answer to this one. So starting with the integral of cos of 5x minus 2 dx, the integral of cos is sine. So we have sine of 5x minus 2, but I'm now going to need to divide by 5. And the reason being, if you take the derivative of sine, the straight derivative of sine of 5x minus 2, you will get cos x minus 2. Not cos of 5x minus 2. But this is a composition of functions, so I'm also going to have to multiply by the derivative of the baby. And the derivative of 5x minus 2, of course, is 5. So if we don't correct for that by dividing by 5 here, we will not get the correct integrand back. It will be 5 times the correct integrand. So that's why I needed to divide by 5 there. That gives me 1/5 sine of 5x minus 2. The antiderivative of secant squared is tan, so minus 3 tan x, the 3 coming from there. And going backwards on this exponential, it was the exponential, but then we'd also have to divide that by the derivative of the exponent in this particular case. And this is only going to work because this is linear. If it was x squared, it would be much more challenging. We'll handle those antiderivatives or integrals later. So this should give me e to the 5 minus 4x all divided by negative 4. 10 divided by negative 4 becomes minus 5 halves. E to the 5 minus 4x. And again, we can't forget the plus c. Can't forget the plus c. All right, last example for the first half of the lesson. Car is traveling with a velocity, initial velocity of 24 meters per second. It starts to slow at time 0. Constant deceleration of that. Find the velocity at time t and the distance the car travels before it stops. If you don't want any hints whatsoever before you attempt to solve this, I would suggest you pause right now. If you want a couple of hints, I'm going to start by suggesting that velocity should be the integral of acceleration. And I do believe, let's say, if it was acceleration, I'm just going to put meters per second squared. And this would be time here. And I know if you took physics with Mr. Hanta, he had you find the area under a curve. So let's say you're finding the area under a curve. Then your units in this one direction would be meters per second squared. And then you'd be timesing that by seconds, because we're doing dimension in this way is seconds, and the dimension in this way is meters per second. And when you multiply those together, or meters per second squared in this dimension, because this is an acceleration, when you multiply these two together, you'll get meters per second. So meters per second squared times seconds is meters per second. So if you integrate velocity with respect to time, if you integrate acceleration with respect to time, you'll definitely get velocity. Now remember, you're going to have a constant added to that. So you have to try and figure out what the constant is, but you can do that because they gave you this piece of information here. And then if you take the integral of v at t, the integral of velocity with respect to time, that should give you your position function, and that's the function you need if you're going to figure out how far the car travels before it comes to a halt. So that's the end of my hints. I'm going to pause just as a reminder. You should have to try and solve this now, and then I'll take it up with you. All right, so finishing this off. I don't know why I put a dv there. That should say dA dt. Is equal to -6, because that's the change in actually no, that's right. That's the change in velocity with respect to time. Never mind, that was correct. So if I'm going to talk about how velocity is changing with respect to time, that indeed is acceleration. I did say that velocity would be the integral of acceleration with respect to time, so that's what I plugged in there. The integral of -6 dt would be -6t plus c. But now we're going to have to handle the c. What are we going to do with the c? They told us the initial velocity was 0, or not 0. They told us the initial velocity was 24. That means v at 24 is 0. So 24 should be equal to -6 times 0 plus c. That's going to give me that c is equal to 24. So the velocity over time can be represented by this function, -6t plus 24. Acceleration with respect to time is represented by -6. Velocity is now -6t plus 24. And now I need to find my position function because I can't answer distance questions without it. So I'm now going to suggest that s at t is the integral of -6t plus 24. Notice that's velocity. These should be lowercase v's, but I'm not going back and fixing that. Lowercase v with respect to time. So the integral of -6t is -3t squared. Notice if you take the derivative of that, you get -6t back, plus 24t. The derivative of 24t, of course, is just 24, so I'm matching the integrand, then plus any constant. So I now have my position function. Now it says how far does the car travel before it comes to a halt? So I need to know at which point in time the car is stopping. So now I'm going to figure that one out. When does the car stop? Well, if the car stops, then s at t, let me note that there, s at t would be 0 when the car stops. So now I have the position function. I can figure out when the car is stopped. No, sorry, not s at t. What am I saying? It should be v at t. If a car is stopped, the velocity is 0. So v at t is equal to 0. So 0 is equal to -6t plus 24. That gives 6t is 24. That gives t is 4. The car is stopped at 4 because v at 4 is 0. And if the velocity is 0, we're not moving at that point in time. So that means now I need to find what my position is at 4 seconds, because that is when the car stopped. The car comes to a halt at 4 seconds. I'm now going to find s at 4 by plugging into here. That should be an exponent. So -3 times 4 squared plus 24 times 4 plus c. All of that gives me -4 plus 96, which gives me 48 plus c, c being my initial position. So how far have I traveled? I'm 48 meters away from my starting point, so I must have traveled 48 meters. All right, so that's the end of the first part of this lesson, looking at antiderivatives. And I will record the second part shortly. So if you've made it this far, again, thank you for watching, and don't forget to like and subscribe.